For you, I'm even sadder than you. I'm 3 times sadder than you.
Rarely have I thought,
Do you guys want to stay after school?
this teaching gig isn't for me.
No, I'm going in during encore on Monday, and I'm gonna go see double check. So I'm missing that meeting.
Okay.
I'm missing that meeting. What meeting? For Sweden.
Oh, say, can you? Maybe we all need to meditate for a second. Only let positive thoughts
No,
roll.
it says you who got away with it.
Why do you always get mad at me and not Gracie? This is just so.
Gracie doesn't say anything.
I don't say anything either.
No shame about Ella. Not you.
Yeah.
You're not in this conversation.
Ella's just being really rude today.
It's like, what are we talking about? Okay, is the camera
Yep,
going?
so rude.
Yes, it is. It's been running.
Okay. All right. So here's the lab that you're going to do. So this has become known as like the cowboy/cowgirl lab. So what you're going to do is pretty simple. You're going to take a piece of string. You're going to run it through a piece of tubing. And then you can take this and swing this around and let go of it, and then you can make the mass appear to hover, okay? And you can change the dynamic. You can make it go a little bit faster, okay? Or you can slow it down,
Wow.
okay? And you can get this action going, okay? All right? So here's going to be the basic idea. The key assumption that we're going to make at the beginning is that there has to be some centripetal force. How do you know that there's a force acting on the rubber stopper?
It doesn't go in a straight line.
Bingo. It's accelerating, right? And so remember, if you change either the magnitude or the direction of the velocity vector, you're accelerating, okay? Because the rubber stopper at any given point wants to turn into a projectile and go off on a tangent. So there's a couple of things that we're going to look at. First off, we're going to start with this idea. So today's lab is brought to you by this equation. That centripetal force equals mv squared over r. So basically, we have 4 variables: centripetal force, mass. Now, let's make sure everybody's cool with this. This mass is the mass of the stopper, okay? Because you're going to have 2 different masses. So the reason that we use the mass of the stopper is because that's what's going to go in centripetal acceleration. Okay, so that's the mass of the stopper. V obviously is how fast it's going, and then you have the radius. So you're going to run 3 different sets of trials. And basically, we're going to keep, at any given instant, 2 of the variables constant. I want to change the other 2. Okay, so keep this in mind. In all of the trials, 2 variables are always going to be constant, and 2 of them are always going to be changing, okay? So what you'll see is that velocity is like the great equalizer. That's what we're going to use to balance out both sides of the equation. So, for example, let's say this is a 200-gram mass. So when I've got that 200-gram mass and hooked that up to the string, and as that thing goes around, here's what we're going to assume, is that 0.2 kilograms is being pulled down by the gravitational field. So that 0.2 kilograms times 9.8 meters per second squared gets you 1.96 newtons. So what we're going to assume is that as that thing is going around, there's a 1.96 Newton force acting. Which direction does any centripetal force act? Inward at a right angle to the velocity vector. Now, you'll notice as this thing goes around, okay, gravity is pulling down on this. That's what's creating that inward force. There is no force emanating out, pushing the rubber stopper out, okay? As long as I've taught physics, I still don't have the superpower to emanate a force field to push the rubber stopper out, which would be cool.
You tried to take my peanut butter and jelly sandwich.
Yeah, I should take mine at lunch.
You didn't eat it at lunch.
I want half of it.
Do you know why I don't teach freshmen?
Because they're always hungry.
No, that's the least of my worries. Okay? So here's the deal. As this thing goes around, there is no outward force pushing on the stopper. What does the stopper want to do? Wants to keep going in a straight line. So what we're going to assume, listen to me, what we're going to assume is that the weight of whatever's hanging down here is what's creating the centripetal force to keep the rubber stopper going around in the circle, okay? So, in this situation, if I had that rubber stopper going around, and here's this tube, and here's a 0.2 kilogram mass, we're going to assume that that's creating a downward force of 1.96 newtons, which is also what's creating the centripetal force. So this column here, where it says to the right of the radius, where it says centripetal force, that's the weight of whatever is hanging down. So on the first 4 trials, I kind of give you some guidance. You're going to use 0.1, 0.2, 0.3, 0.4. So on that second trial, where it says 0.2 kilograms, that centripetal force is going to be 1.96 newtons, okay? So your centripetal force column, all you do is take your hanging mass column, multiply that by 9.8 meters per second squared, boom, there's your centripetal force column. So what you're going to do on trials 1 through 4, you're going to make the centripetal force get bigger and bigger and bigger, because you're going to hang more and more weight from the end of the string, okay? So the centripetal force is going to be increasing on trials 1 through 4. M is going to be the mass of the stopper. So to get the mass of the stopper, I'm going to have an electronic balance back there, take the mass of the stopper, put it on there, and get a number. That's going to be measuring in grams. How are you going to convert from grams into kilograms? Divide by 1,000. Okay, don't divide by 100. That's the most common mistake that's made in this lab. Divide by 1,000. Okay, and you'll see that I've got a tub back there of different size stoppers. For this first 4 sets of trials, choose like a medium-sized stopper. Don't go real small. Don't go real big. Kind of go like a nice medium-sized stopper. When you tie this on, make sure that you tie it on securely. I don't want this thing turning into a projectile motion lab, okay? Make sure it's tied on. If you're not sure, ask me, okay? And then you're going to tie like a little loop on the end, and that's what's going to go on the other end. So the centripetal force, that's easy to measure. Not a big deal. Weight of what's hanging down. Mass of the stopper, easy to measure. Put it on the scale. Not a big deal. The radius becomes problematic because, let's say, for example, I get this thing up and going like so, and I say, hey, Cooper, let's try and measure the radius. Well, that's going to be a little bit tough to do when this thing is running around over the top of my head, and Cooper's kind of meter stick going like this, it's not going to happen, okay? Somebody's going to get hurt, lose an eye, whatever. So here's what you're going to do to get the radius. What you want to do is lay this out. So let's say that you want a radius of 0.8 meters, which is going to be this first one. So what you want to do is take your meter stick, put that end on the center mass of the stopper. Okay, not the end, center mass of the stopper. And then you're going to take this, now you're going to go like this, and what you're going to do is you're going to put the top edge of the tube at the 80 centimeter mark. Okay, so that way, that's what you're going to do to get your radius. So that's going to be like this. Then what you want to do, when you get to that, then you're going to take a marker, and you're going to make a mark on the string. So, we got a pen or pencil?
Pencil?
Hold on.
I have a
I
highlighter.
got this. Never mind, I got this. So you're going to make a mark on the string like this, okay? So there's going to be this mark. So what's going to happen is whoever is doing the swinging, so they're going to go like this, And the reason that you make that mark at the bottom is that then you can get this going until that mark is at the bottom of the tube. So that way I know when that mark gets to here, that distance from the top of the tube out to here is 0.8 meters. So that's what you want to do. Don't put the mark up here, because if I'm swinging this thing around, I won't be able to see when that mark gets up there, but I'll be able to see it when the mark gets to the bottom of that tube, okay? So once that gets there, then that way I know that distance up there is going to be the 0.8 meters. That's the second most difficult one to measure. Boom, there you go, you got that. The hardest one is going to be the velocity. So here's what we're going to do on the velocity. So this thing, oddly enough, is going to be moving around in a circle. Okay? So basically, we're going to go, oh, the velocity is going to be distance divided by time. Well, how can we find the distance that the rubber stopper is going to travel? Circumference of a circle, otherwise known as 2 pi r. Okay, that's kind of cool. So we have the radius. Got that. So we can calculate the circumference. Then we're going to divide by uppercase T. This is the hardest part of the whole lab, is measuring the period for one revolution. So the technique is, and you want to have at least 2 people in your group timing this thing. At least 2. So what you want to do is everyone do the swinging part. Okay, they're going to get this going like this. Okay? Boom. I got a nice steady revolution. And you want this to be horizontal. You don't want something like this going. Okay? Bad form, right? You want it to be, when you start this off, it's about, if you're going to do the swinging, hold this hand, kind of get it going, and then when you get it fast enough, you'll almost feel that thing like begin to lift off, okay? So you're going to have something like this, where you have a nice, steady, even speed. So it's going to be tough to precisely measure just 1. So what we're going to do is we're going to measure 10, okay? So this is, as odd as this seems, the hardest part of this lab is counting to 10. And you're going, seriously, Burkham? No, I swear to God. If this lab goes south, it's because somebody can't count to 10. So if you're going to be doing this, so here's your technique. You're going to have your phone, stopwatch, whatever. Okay, so I'm going to have this going. So you want to start your stopwatch, and then you're going to start it when it's here. That's when you stop, when you're going to start your timer. But then when this comes around, that's going to be 1. When it goes around again, that's 2. Okay? So don't hit your stopwatch and go 1 at the same time. So you got to hit your stopwatch and then go 1, 2, 3. Now, a couple words of advice. Don't count out loud. Okay, we all know you can count to 10. You're seniors at Mays High School and taking like the highest level science class. You don't show off. We know you can count to 10. Because what happens is that you got other groups that are trying to do this thing, and you're going 1, 2, 3. Okay, and people are going to want to hurt you. All right, so don't count out loud. But it's also some intense timing, and so you kind of get people doing what I call the guppy count. So they'll be going. Okay, they're like guppies underneath the water trying to, grasp for air. You can do that. You can do the head nod thing. Okay, it's cool if you want to do that, right? Just don't count out loud. The real intense timers, what they will actually do is they will lay on the floor and they will count the revolutions as it goes past like a seam on a seam, like a seam in the ceiling. Okay, so they'll go start it. 1, 2, 3. So this is why you want to have at least 2 people timing this. If you time this, and let's say I get 1.6, and let's say Dime gets 1.4. Don't take the average. That is too far apart. Either I counted to 10 and Dime counted to 9, or there was a difference in the number of revolutions, this lab is a home run, unless you can't count to 10. Okay? But I swear to God, that is the biggest thing where this lab goes south, is your ability to count in time precisely 10 revolutions. Okay? Seen it before 100 times. Literally, if there was a big difference, don't just say, well, just take the average. No. Okay? Somebody didn't count to 10. All right. So you're going to have your centripetal force column. Like on that first one, that would be 0.98 newtons. 0.1 times 9.8, yeah, 0.98. Period. That's going to be the time for one revolution. Okay? So then you got 2 pi r. That's going to be your circumference. And then you're going to take your velocity, so you're going to take that circumference and divide that by your period for one revolution. Now, let's talk about the trend that you should see. So this also turns into a nice mathematical model. So if you look at these first trials, okay, come back here. If you look at these first trials, and this is going to be the model that you're going to use for all of these, okay? So you're going to have centripetal force equals mass v squared over r. So on trials 1 through 4, this is going to be the mass of the stopper, and that's going to be the radius. So in trials 1 through 4, that ratio of mass of the stopper to radius is going to be a fixed value. You're not going to change the mass of the stopper, and you're not going to change the radius. So if you really wanted to get fancy, you could have that as a constant. You could take the mass of the stopper and divide it by 0.8 meters, and that's just going to be a numeric value, okay? And it's going to be a ratio of the mass of the stopper to that radius. So you could write this in a mathematical class. You would say, oh, centripetal force equals kV squared, okay? Because that's a ratio of mass to radius. It's just a constant, right? So here's the deal. So as your centripetal, this is what you want to be able to think through. As your centripetal force is going to get bigger and bigger and bigger, and that's what's going to happen. You can go from 0.1 to 0.2 to 0.3 to 0.4. So you're going to put more and more weight on the bottom of that string. So as that centripetal force gets bigger, what has to happen to your velocity?
It has to get bigger.
It also has to increase, right? Because both sides have to remain the same. So as your centripetal force goes up, your velocity has to go up. Okay, it's a direct relationship. But, is it going to be in 1-to-1 ratio? If I double my centripetal force, am I going to double my velocity? You shake your head no. Why, Miss Yale?
Because it's by a factor of this, isn't it the square root of 2?
Well, it's just a squared value, right? Okay, that's the short version. Because velocity is squared, okay, it isn't going to be a 1-to-1 ratio because of the fact that it is squared. So if you were in a math class, let's say you were in a pre-calc class or whatever, and you said, hey, we're going to graph y equals kx squared. What would that look like? If you were in a math class, what would y equals kx squared look like? Parabolic curve like this, right? It would go something like this. That's what this graph should look like, okay? Because of the fact that it's going to be a parabolic relationship. So, now, when you get to trials 5 through 8, on 5 through 8, you're going to keep the centripetal force the same. So on 5 through 8, pick one of the masses that you used up above, okay? I'd recommend maybe 0.2 to 0.3. 0.4 gets a little weird because you have to go really, really fast. 0.1 is a little bit slow. So I'd either pick like 0.2 or 0.3 kilograms. So here's what's going to happen on trials 5 through 8. So on 5 through 8, oddly enough, you're going to look at centripetal force equals mv squared over r. So on 5 through 8, you're going to keep the centripetal force constant. This number is going to stay the same. Okay, 0.2 kilograms, 0.3, whatever one you pick. You're going to keep the mass of the stopper the same. There you go. That's not gonna change. But now what we're gonna change is the radius, okay? So what I would recommend when I say change the radius, I mean change the radius, okay? You want at least 10 or 15 centimeters difference in these trials. In other words, don't go like 0.50 to 0.55 to 0.6. You want a noticeable change. Maybe start at 0.4, 0.55, 0.7, something like that, okay? You want at least 10 to 15 centimeters of change in that radius. Now, here's the deal. Think this through. I'm going to make the radius bigger and bigger and bigger. So as my radius gets bigger, and keeping in mind that my centripetal force is the same, okay? This number is staying the same. So Maggie, and the mass of the stopper stays the same. So as the radius gets bigger, I'm dividing by a bigger number, Maggie, but I want the same centripetal force. So what has to happen to my velocity? It has to get bigger. But again, is it going to get bigger in a 1-to-1 ratio? No, because the velocity is squared. Okay? So what you should see on trials 5 through 8, as the radius increases, your velocity should decrease. Now, that gets a little bit tricky, and there's a couple of different ways you can handle this one. I've got different colored markers back there, so what you could do is that when you're making your marks on the string, put those into different colors, okay? So who's ever doing the swing, this radius matches this particular color, okay? Because if they're all the same, then that's going to be really tough to keep track of. So make sure that you know which radius that you're using. Okay. Now, on the last one, you're going to, oddly enough, start with this. On those last set of trials, again, you're going to keep the centripetal force the same. Okay? So you can use the same centripetal force on trials 5 through 12. Okay? If your group says, hey, let's use 0.2, 0.3, whatever that is, you can use that on all trials 5 through 12. Now you're going to keep a radius constant, okay? And you can use one of the radiuses, like radii that you already chose. Okay, you don't have to pick a completely different one. You can use a different radii. But then we're going to alter the mass of the stopper. Okay, so I've got little small stoppers, I've got bigger stoppers, okay? I don't recommend that you take like 5 stoppers and tie them all together, okay? Don't ask to borrow Hank the bowling ball and swing Hank on the end of the string. Don't get me wrong, that's extreme, centrifugal forcing, but that's a bit much, okay? So you're gonna have different masses of the stopper. You can, if you have like a couple of small ones or like a small one and a big one, you actually want to tie them together, that's cool. But don't go like too extreme. Now, think this one through. Topher Knizia. On 9 through 12, I'm going to keep the centripetal force the same, and I'm going to keep the radius the same. So Topher, as the mass gets bigger, I want the same centripetal force. What has to happen to the velocity?
Get smaller.
There you go. Okay? So this is the only one that's an inverse relationship. All the other ones are some version of a direct relationship. Okay? Because this is the only one where as one value gets bigger, the other one becomes smaller. Now, let's think about this. Let's go back to those first set of trials where centripetal force was getting bigger. Okay? So here's what I want you to think through. And if you can think this through, it kind of gives you an idea of what your data should look like. So on trials 1 through 4, here's what's going to happen. You're going to create a bigger centripetal force, which is going to equal mv squared over r. And we said that the velocity had to get bigger. Okay? Now, let's do a little bit of a sub-calculation. As your velocity gets bigger, and that velocity is going to be calculated by 2 pi r over t. Okay? That's what I want you to think through. So on trials 1 through 4, I'm always going to have the same radius. So the circumference of that circle isn't going to change. That's a fixed value. Okay? So what's the only way I can make my velocity get bigger? Dyne. To create a bigger velocity, what's gonna happen to that value of t?
It's gonna get smaller.
It's gonna get smaller, okay? It's going to get smaller. So what you should see as a trend on trials 1 through 4, the time for 10 revolutions is becoming smaller and smaller and smaller. Because you gotta swing that faster and faster and faster to create more and more centripetal force, okay? So if you can kind of think that through in terms of your data, that might help you to see that trend. So what you're gonna do on the back side is that you've got over here, we'll kind of go through this. So on trials 1 through 4, you're gonna make a graph. And you're gonna put velocity on the x-axis, and you're gonna put centripetal force on the y-axis. And on the first 2 graphs, I tell you in the instructions, you're gonna start these graphs at 0, 0. Okay, the third graph is the only one that you want. So none of these are gonna be linear. None of these graphs are gonna be linear, okay? You should see some curves to them because it's all dealing with v squared, okay? So your first graph should look something like this, roughly. Now, if you get your data and you've got like 2 of your points are like this, and your 3rd point is up there, and your 4th point is back down there, you did something wrong on that 3rd trial, okay? If you do these trials and one of them is a complete outlier, go back and redo that trial. Again, somebody didn't count to 10. Okay, maybe they counted to 11, maybe they counted, I don't know. Now, here's a word of advice. On those first 4 trials, the most difficult technical one is going to be the 4th trial, because that's the one that's going to be going the fastest, okay? So what I would recommend is that maybe you work your way up to that one, okay? Kind of get your feet wet, start, point 1, point 2, point 3, work your way up to that one, because that's going to be the most difficult, because that's what's going to be going the fastest. When you get to 5 through 8, that's when you're going to be changing your radius. Okay, again, choose wisely. Okay, I wouldn't go much smaller than 0.4. Don't try and get one of like 2 meters. Okay, that's going to be a really, really long string. Okay, make sure that you're keeping track of those marks on that one. Then you're going to do those last ones where you change the mass of the stopper. Okay, I'm done. Take your time. Get good data. Okay, this lab is an absolute home run as fast as you can't count to 10. Okay, stop that.